So today's lesson is going to be very important because I'm actually gonna work out the assignment 4 for the first part. And for the second part, actually, I want to talk about how would you solve a most generalized robotic system problem. Also, I want to ask you this question is, are you guys interested in learning how to use SolidWorks to solve robotics problem? If you are, uh, I would be happy to cover a couple of lessons on SolidWorks, because here is what happens. The approximations that we have here, we are considering robot joints to be cylinders. We are considering robot joints to be some prismatic joint, maybe a slender rod, maybe a beam or a bar or something like a very regular shape. However, the actual robots, they are not regular. They are very complex. The material properties are not uniform. Sometimes you have the robot arms. They are partly made up with steel, partly made up with composite. You have a gripper, which is not a completely solid, but it has some mechanisms, moving parts, some holes, maybe some other additional mechanisms. So what I'm trying to say here is the actual robot is complex. So whatever we are doing here is sort of an approximation to the actual robot. So if you want to analyze an actual robot, what you do is you create the CAD model for that robot, and then from the CAD model, you find out the inertia properties and all other mechanical properties and use MATLAB for simulation. Or you can go a step further and you can import that robot into something like Gazebo or something like VREP. Gazebo and VREP are very powerful softwares that allow you to do the robot simulation. So when you go to industry and say, if you start working in an industry as a robotics engineer and you are designing robotic arms, what you will do is you will do some hand calculations and then you will use these sophisticated software tools to analyze the robot. So if there is enough interest, then I would be happy to actually do 1 or 2 lessons, how to do the robot dynamics using commercial softwares. We can use SolidWorks. That's software that is available free of cost to all the students, but you need to have the mechanism plugin installed. So if you go to my ASU My Apps, download the SolidWorks, please install the complete SolidWorks and along with all the add-ons, and you need to have the simulation add-on to simulate a mechanism. You can integrate SolidWorks with MATLAB. So you can design your controller in MATLAB and integrate that with the SolidWorks robot arm. I don't think I will have time for that, but I will at least give you an introduction on SolidWorks and how to perform basic robot analysis on SolidWorks. And then there is another software which is called VREP or Gazebo. Those are also very powerful softwares for dynamical analysis. Now, in today's class, what I want to do is, let me quickly review what we discussed in last class. In last class, we looked at how to analyze the robot arm, wherein you have a revolute joint, you have a prismatic joint, and you have a mass M3 at the end effector. And what we did is we drew the kinematic diagram, we performed the forward kinematics, we eventually performed the inverse kinematics and derived the necessary equations. But when we go to the dynamic analysis, the first step is we identify the locations of masses. So in this robot arm, the masses are at location M1, M2, and M3. Step 1 is to find the position of masses. So for an example, we derived this in last class. We found out for mass M1, we have Px, Py, and Pz. And for that mass M1, and I'm going to write this on the board because I'm going to code these equations in the MATLAB. So I need the equations at the same time. Just need to make sure. Okay. So mass M1 Vx. So I'm going to call this Vx1, which is the velocity, which is minus L1 by 2 sine theta 1 dot Vy1. Vx stands for velocity of mass 1 in x direction, velocity of mass 1 in y direction, which is L1 by 2 cosine that's what happens. Dy1 cosine theta 1 dot and Vz1, which is 0. Then we performed the Jacobian analysis and we found out omega x1 is equal to 0, omega y1 is equal to 0, omega z1 is equal to theta 1 dot. Are you with me so far? These are the velocities. For mass M1, we have M1 is equal to Mx is equal to My is equal to Mz. Because mass M1 is the same in X, Y, and Z direction. However, I x1, I y1, and I z1 are different. I x1 is going to be 0. I y1 is going to be 0, and I z1 is going to be m1 L1 square by 12. Is everyone clear about this? Any questions here? Why so I x1, I y1, and I z1 is equal to 0? Because please understand, this is x, this is y, and z is coming out. So moment of inertia about x, mass moment of inertia about x is 0. Mass moment of inertia about y, it's something, it can be something. The only thing what we are interested in, the mass moment of inertia about z. So I just have to write this somewhere. So this is the CG, this is where the M1 is. Everyone clear about this? Next thing is mass M2. For mass M2, we have Vx2 is equal to minus d2 sine theta 1 dot plus d2 dot cosine theta 1 dy2 is equal to d2 cosine theta 1 dot plus d2 dot sine theta 1 vz2 is equal to 0. Same thing, omega x2 is equal to 0, omega y2 is equal to 0, omega z2 is equal to 0. Now, I have to write mx2 is equal to m2, my2 is equal to m2, mz2 is equal to m2, because the mass is going to be the same in x, y, and z direction. Now ix2, iy2, and iz2. So this is going, iz2 is going to be m2 L1 square by 2, and I2 is not important, and x2 is not important because x2 is 0, y2 is 0. So for that matter, you can just leave it as is. So you don't have to write anything here. Next mass is mass M3. And for mass M3, yeah.
So why is with mass M2, why is the inertia in Z depend on L1? Because isn't that the length of the other segment?
L2. L1.
And why does it not have any rotational speed about Z? Isn't it? If
Oh,
one
yeah,
is rotating-
yeah.
Oh.
So theta 1 dot.
Okay.
So yeah, I think I derived all this in last class. So just make sure that I'm just writing these equations down that we derived in last class.
So is it over 2 over 12? The IZ
Oh, 12. Yep. Cosine theta 1 minus L2 by 2 sine theta 1 dot. And you don't have to copy these. Just open up the notes that you have. Because what I'm going to do is I'm going to actually code these equations inside the MATLAB. And at that time, I won't have these equations in front of me to show you the correspondence between the variables that are here and the variables that are used in MATLAB. So I need both of them at the same time. So when I actually code it, because this coding is going to be, you have to be very systematic. Otherwise, I promise you, it won't be right. So cosine theta 1 dot vz3 is equal to 0. Same thing, omega x3 is equal to 0, omega y3 is equal to 0, omega z3 is equal to theta 1 dot. Okay, mx3 is equal to m3, my3 is equal to m3, mz3 is equal to m3, and ixx, iyy, ixx3, iyy3, and ibz3 are zeros because the radius of gyration is 0. Okay, now it's going to be a little bit tricky for my online students, but I hope you are able to. Can you please move the camera? Yeah, I can move the camera, but I don't know where to move it. Yeah, so, but my recommendation to you is what I have done here is I have done nothing but rewrote the equations that I derived in last class. Now, with these equations, next step is writing the equation for kinetic energy for mass 1. Mass M1, there are two types of kinetic energies. One is the kinetic energy of translation, which is 1/2 M1 Vx1 square plus 1/2 M1 Vy1 square plus 1/2 M1 Vz1 square. So what needs to happen is whatever Vx1 I have, Vy1 I have, Vz1 I have, that needs to go here. So that this will be a long expression. Everyone understands this? Next thing is I need the kinetic energy of rotation, and this is going to be 1/2 Ixx omega x square plus 1/2 Iyy omega y square plus 1/2 Izz omega z square. Are you with me so far? The total kinetic energy, which I call it T. T is the total kinetic energy, which is kinetic energy of translation plus kinetic energy of rotation. Now, I want you to understand that this robot arm is in the horizontal plane. This robot arm is in the horizontal plane. That's why the potential energy is 0. Do you agree with me? If you look at the potential energy, since this robot arm is in the horizontal plane, if I take my datum, if I take my datum to be the horizontal plane, all the z's are going to be zeros. Do you agree with me? So my potential energy, which is V1, is going to be 0. And the reason for that is the arm. So I need to draw this arm. So this arm is in the horizontal plane, and this is where the end effector is. So if I consider this as my datum, all the masses, so M1, M2, and M3, all these masses are about the datum. There is no z, so the finite potential energy of mass M1 is equal to 0. What I need to do is I need to do the exact same thing for mass M2, and this equation will be duplicated. The only difference here, M1 will be replaced by M2, Vx1 will be replaced by Vx2, and so on. And I'm going to write this. And I would strongly recommend that when you are working out the problem, at least for first few times, please complete these steps. Y2 square plus 1/2 M2 Vz2 square. Kinetic energy of rotation is 1/2 Ixx1, Iyy1, Izz1. Again, 1, 1, 1. So Ixx1 omega x is 2 square plus 1/2 Iyy2 omega y2 square plus 1/2 Izz2 omega z2 square. T2 is kinetic energy of translation of 2 plus kinetic energy of rotation of T. And V2 is going to be 0. Are you with me so far? The last part is for mass M3. Same thing, but please understand, since Ixx3, Iyy3, and Izz3 are zeros, kinetic energy of rotation for mass M3 is going to be 0. Not because omega x2, omega y2, omega z2 are 0, because Ixx3, Iyy3, Izz3 are 0. So kinetic energy of translation for 3 is going to be 1/2 m3 px3 square plus 1/2 m3 py3 square plus 1/2 m3 pz3 square, and kinetic energy of rotation is equal to 0 because all i's are 0, and T3 is going to be kinetic energy of translation of 3 plus kinetic energy of rotation of 3. V3 is equal to 0. Everyone understood this setup? Now, if I want to formulate the Lagrangian L is total kinetic energy minus total potential energy. This is nothing but T1 plus T2 plus T3 minus V1 plus V2 plus V3. Everyone understood this?
And all of the V's, V1, V2, V3 are 0 because we're operating the XY plane.
No, because this is the datum and mass is on the datum, and mass will always be on that horizontal plane. Okay. Now, next step is I'm going to take these equations and code these inside the MATLAB so that the MATLAB can take this Lagrangian, find out the differential equations of motion, integrate those differential equations of motion, and provide the solution. Everyone understood this? Online students, any questions? Are you able to see? I don't think you can see the entire screen, but I just want to give you a chance to see the equation. And these equations are nothing but the same equations. The potential energies are zeros because if you look at this guy, if you look at, yeah, it's slightly askew, of course. Because mass M3, M2, and M1, they are in the horizontal plane, and I am assuming the datum is aligned with M1, M2, and M3. That's why there is no potential difference. That's why V1 is 0, V2 is 0, and V3 is 0. Okay. Now, what I want to do is, we got these equations. Now, bear with me for a second. I want to share the screen and I want to code this inside MATLAB. Okay. Now, are you able to see my MATLAB screen? Okay. Now, this is going to be a little interesting. Can you see my whiteboard and MATLAB screen? Online students? Yeah. Okay. Now, because what I want to do is I want to go line by line and show you which variable in this equation is coded inside the MATLAB script and how. So before you even start coding, you need to have this stuff done on the piece of paper. Before even you start using MATLAB, these equations need to be written down. First and foremost, I want you to tell me how many joints do we have in this robot arm? We have a revolute joint R and we have a prismatic joint P. Do you agree with me? So we have two joints. What are the joint variables under consideration? Joint variables are, and my online students, I hope that you are able to see my screen. This is theta1 and then this is D2. So first and foremost, I have to identify the states, and this is very important. This is needed for MATLAB code. So here I need to know the states. States are the angular displacement of joint 1. Angular displacement of joint 1 is theta1. Angular velocity of joint 1 is theta1 dot. Linear displacement of joint 2, which is D2, and linear velocity of joint 2, which is D2 dot. Yeah, the screen is not showing. Yeah, unfortunately, that is what happens. So please try to attend lessons in class. But so the states are theta1 dot, D2 and D2 dot. So first line of code in your MATLAB script is identification of the symbolic variables, which are nothing but the states. So states are type. I want you to type whatever it is on the line number 4. SYMS, which is the symbolic variable, TH1, TH1D, D2, and D2D, which stands for theta1, TH1, TH1 dot, D2, and D2D. Are you with me so far? It is extremely, extremely important that your sequence is going to be like the first joint velocity, second joint variable, second joint velocity variable. Everyone understood this? Next, D2D for the link with D2 is the extension of joint 2. So D2 is the extension of joint 2. Okay. Next, if you want to define the gravitational constant, I have just added the value of G for the reference 9.81. To be honest with you, we don't use it, but I just left it over there. Next step is I want to define the inertia properties of mass M1. So for mass M1, I have M1 is equal to 1. That mass will be the same mass whether you consider that in the X direction, Y direction, or Z direction. That's why I'm just saying M1 is equal to 1, which goes without saying that that is equal to MX1, MY1, and MZ1. Everyone okay with me? Next thing is I'm saying L1 is equal to 1. I need to clarify something here. And this point is important. In this problem, it doesn't matter, but if you solve another a problem which is more complicated, it matters. So I want you to understand. In this particular problem, what we have is you are looking from top. You are looking from top, and this is the link. Now, what I'm going to show you here is this link has this width, this length, and since W is much less than L, I have, so always imagine inertial axis at the centroid, and this is going to be the x-axis, this is going to be the y-axis, and z-axis is going to come out like this. So what you have is, since W is much less than value of L, I have IZ1 is equal to M1 L1 square by 12. Everyone understood this? Because ideally it should be M1 in the parentheses L1 square plus W1 square, parentheses complete. But since W is much less than L, I have this M1 L1 square by 12. And in this code, what I have done is I tried to be, well, sort of sloppy, and I did not write it over here. But let me complete this argument here. Ix1 is 0. Iy1 is M1 L1 square by 12. So in this code, this is this guy, copy. And some of you may ask, so some of you may ask me, where did this come from? So for that, what I'm going to ask you is, I want to ask you to refer to the mass moment of inertia equations that I derived in last class. And you will remember that Iyy is L1 square plus H1 square multiplied by M1 divided by 12. I need to be, this is an important point, so I need to clarify. So what I'm showing here is, this is X, this is Y, and Z is coming up. So using this sign convention, this is L1, this is W1, and this is H1. So you would substitute that in there. You will repeat the same process for the second mass. For second mass, M2 I've assumed to be 1 kilogram. L2 I've assumed to be 1 meter. Ix2 is 0. Iy2 is going to be same guy over as this. So copy. L2. And then Iz2 is going to be M2 L2 square by 12. So these are the inertia properties of mass 2. It goes without saying, I'm just saying M2 is equal to 1, but that means MX2, MY2, MZ2 is equal to M2, that is equal to 1. Everyone okay with this so far? This stuff is super important, by the way. So make sure you understand. The last part, I'm just saying M3 is equal to 1. Because that M3 is same as M3, MX3 is equal to MY3 is equal to MZ3 is equal to 1 kilogram. That's just a point mass. So the length is equal to 0. So all the I values for that mass M3 are going to be zeros. Everyone understood this? Yeah.
On mass 2 right there, is it supposed to be I2 or?
This is L2.
Okay.
This is M2, and this is the length.
Okay.
Length of the link.
Okay.
Yeah.
So on the homework, you just specify M1 and M2. So should we add in this M3 to what for now?
Don't get it. So basically, I think I try to make the homework problem simple. I just gave you I1, I2s, and I3s. Then I gave you I1 is equal to 1, I2 is equal to 1. Yeah, I try to make it simple, but this is the most general form.
Okay. So when we're solving the homework, how do we find out the component? Like the
You can either find the component or use the value that I have given you.
So we just use I1. If I1 equals 1, we use that for the X, Y, and Z. Okay.
No. Hold on. I will answer that question. Let me discuss.
Yeah.
So because in that problems there are some additional things that I need to discuss. So M3 is equal to 1. Now the next line is what I want to do is I want to find out the Vx1. So please look at the equation for Vx1. That equation is L1 by 2 sine theta 1 multiplied by theta 1 dot. Can you see that that is the same expression on line number 24? Are you with me so far? Type it. Next line, I have the equation for dy1. This equation is the same equation that I have written over here, which is L1 by 2 cosine theta 1 dot. Yeah.
L1 by 2 have brackets.
L1 by 2 has what?
Brackets so that it doesn't just.
No, that's okay. It doesn't matter. Because when MATLAB is going to evaluate that, it will substitute L1 is equal to 1. So that will just be a number. So that's it. Now Vz1 is equal to 0. Now please understand omega x1 is the angular velocity about this guy. Omega x1 is equal to 0. Omega y1 is equal to 0. Omega z1 is equal to theta 1 dot. Please score this. That way your assignment will be done. Yeah.
And then why aren't we using just like the diff function, like just diff pH1? Why are we writing pH1 d instead of just the derivative?
Don't do derivative because what we have done is the Euler-Lagrange code expects states, and the states should be explicitly defined. So our states are first joint variable velocity, second joint variable velocity needs to be expressed as the symbolic variable SYMS. Remember the first line was theta TH1, TH1D, D2, D2D. So that's why I didn't use the diff code. There is a way that the whole thing can be done with MATLAB using diff, but that I will explain in next class, not now. Let's go step by step. Okay, so omega x1, omega y1, omega z1 is defined. Next, I have to program the kinetic energy of translation for the first mass. Kinetic energy for translation for the first mass is 0.5 m1x vx1 square. Since m1x is equal to m1, I just substituted m1. 1/2 my1 vy1 square and just substitute m1. 1/2 mz1 vz1 square. I substituted m1. So that expression on line number 32 is this equation. Are you with me so far? Then on line number 33, this is the kinetic energy of rotation. Please understand, kinetic energy of rotation, Ix1 is different than Iy1 is different than Iz1. So I need to specify half Ix1 omega x1 square, half Iy1 omega y1 square plus half Iz1 omega z1 square, which is this expression. Are you with me so far? Type it. I'm not going to email this code or put that code in the chat window. Or you can do OCR, by the way, take a picture and do OCR, but that won't help you. Next line is the total kinetic energy is kinetic energy of translation plus kinetic energy of rotation. So line number 35 is the kinetic energy of translation plus kinetic energy of rotation. That is the total kinetic energy. Am I going to post the recording? Yes, I'm going to post the recording. V1 is equal to the potential energy. For this robot joint, the potential energy is 0 because I'm assuming this robot arm to be in horizontal plane. If some of you think that this robot arm is in the vertical plane, please understand your V1 and V2s and V3s will be non-zeros. Okay, so don't make your life complicated. Write that this robot arm is in the horizontal plane. Draw the kinematic diagram which I have drawn. That way your V1, V2 and V3s will be zeros. Are you with me so far?
When we draw the kinematic diagram, do we need to specify the coordinate axes on that?
If you want to forward and inverse kinematics, you have to. That is the first two parts, right?
Yeah.
You know that answer to that question before you ask that question, right? Okay, so quoted. Is that some short form for BRB or I don't know what? Okay, so Vx2 comes from that expression d2 sine theta 1 dot d2 dot cosine theta 2. So that is the expression for V2. So V2 sine theta 1 dot d2 dot cosine theta 1, and that is this equation. Then Vy2 is the equation that I have written over there, d2 cosine theta 1 dot plus d2 dot sine theta 1. This is that equation. Are you with me so far? Right. And Vz2 is equal to 0. Yeah, the assignment 2 will be due next Wednesday. Assuming I finish the path planning and trajectory planning by Wednesday. If I don't finish it, I will give you explanation. Don't worry about it. Just focus on learning the concept. It's very important. The last part is omega x2 is 0. omega y2 is equal to 0 and omega z2 is equal to theta 1 d. So this kind. Are you everyone up to this point? Okay, code it. That will save you a lot of headache later. Now, the next part is I need to write down the kinetic energy for translation for mass 2. Kinetic energy for translation for mass 2, which is this guy. And please note mx2 is equal to my2 is equal to mz2. So that's why the kinetic energy is this guy. Then kinetic energy of rotation is Ixx2, Iyy2, Izz2. That expression is over here. 1/2 Ix2 omega x2, 1/2 Iy2 omega y2 square, 1/2 Iz2 omega z2 square. Are you with me so far? Okay. Then next part is total kinetic energy. Is kinetic energy of translation plus kinetic energy of rotation. Then the potential energy for mass 2 is 0 because it's in the horizontal plane. Now, what we need to do is we need to go to mass 3. In mass 3, I kind of took the shortcut. So I just wrote Vx3, which is the equation which I have derived over there, which is d2 sine theta 1 dot, d2 dot cosine theta 1 minus L2 by 2 sine theta 1 dot. Py3 is d2 cosine theta 1 dot, d2 dot sine theta 1 plus L2 by 2 cosine theta 1 dot. Can you see that that is the same expression that is coded over here? And then Vz3 is equal to 0. Kinetic energy of translation is given by 1/2 m3 vx3 plus 1/2 m3 vy3 plus 1/2 m3 vz3. Kinetic energy of rotation is equal to 0 because the inertia properties Ix3, Iy3 and Iz3, Ixx3, Iyy3 and Izz3 are zeros. Everyone understood this? Now what you do is you write down the total kinetic energy and you get here. The last part is I have this total potential energy V1, V2, V3, and then I have the total kinetic energy, which is T1, T2, and T3. T1, T2, and T3. So this is all T's. And finally, what I do is I form the Lagrangian, which is L is equal to T1 plus T2 plus T3 minus all the potential energies. Yeah.
Can you move the shaft to the left or? Can you even zoom out like that and like line 46?
You want me to zoom out the whole thing, or is
I mean, zoom also, more line can be visible.
more line can be visible? But okay. Clearly now no lines are visible. Okay. This is the best I could do.
Scroll down a little more.
Yeah. So everyone is good till Lagrangian. Now the next part is we have to use the Euler-Lagrange code. And now I want to specify a few things. This X are the states or the symbolic variables that we defined. You can't flip the sequence. Remember, we defined our symbolic variables as TH1, TH1D, D2, and D2D. So these states should be in the same sequence. That will be defined as X. Can't change this variable. This has to be X. Next is generalized internal forces. And these are zeros. So now at this point, I want to tell you what are these generalized internal forces. Imagine this robot arm, the rotary joint or the prismatic joint or the revolute joint, they have some internal damping, or if they have some friction. So these are internal forces, which means there are some elements internal to the system that are dissipating energy. So those are generalized internal forces, which means if this robot arm would have had some damping, that damping would enter here. This would be the damping for the revolute joint. Here would be the damping for the prismatic joint. Everyone understood this? In our robot arm, right now, our internal forces are zeros. We assume that robot arm to be ideal robot arm. No friction, no dissipation, nothing. So that's why these are zeros. If you look at the robot arm, in that robot arm, you would have a rotary motor which would rotate the revolute joint, and then you have a linear transducer that would extend or contract the prismatic joint. So you would have a rotary actuator and you have a linear actuator. Those actuators would go over here because those are external forces. Those external forces are nothing but the forces on the joint. Everyone understood this? And this is an important point. Remember, some time ago, I gave this long derivation of Jacobian, and I said external forces giving rise to motor torques. Remember, I derived the equation for motor torques, tau 1 and tau 2. Remember that? From method of virtual work. Those tau 1s and tau 2s are the motor torques. It could be a rotary motor or it could be a linear actuator. Those torque values would appear here. Instead of zeros, this would be the torque on the first joint given by the first motor. This would be the force on the second joint given by the linear actuator. Everyone understood this? And this is very important that in this problem, the torques are zeros, which means this robot is not controlled. There is no motor. This robot is free to move as is. In the next few lessons, what we are going to do is we are going to control this robot. And what do I mean by controlling the robot? Controlling the robot is adding the appropriate torque values or appropriate force values at the joints so that that robot can perform particular operation. So if you want that robot to go from point A to point B and extend, what you would do is you would add a torque here and then you would add a force here so that the robot can rotate and the robot can extend. Everyone understood this? So this is the joint torque for joint 1. This is the joint force because the second joint is a prismatic joint. It cannot have torque, it can have force. Torque on the first joint, force on the second joint. Everyone understood this? And finally, you have the R, which is the energy dissipated and damping. Okay. And then if you move up, there are parameters. And right now we are not having any parameters. If you actually parameterize the robot arm, so for an example, if the end effector mass is changing. So for an example, that robot arm goes to point A, picks up something, goes to point B, which means the robot arm mass is changing. That will be defined as this parameter, and then you will change that parameter in your code. But we will look at that not now, later. But right now, this is how the equation is set up. Now we have to call this function, which is called Euler-Lagrange. So this is the exact script that you need to run. You will call this Euler-Lagrange code. First value is you have to specify the Lagrangian, states, internal forces, external forces, dissipation elements, parameter. M indicates that create the MATLAB file. S indicates create the Simulink function. ODE1 says the name of the MATLAB file and name of the Simulink function will be ODE1. Everyone understood this? That is how the code generator should be invoked. And it is important that you should have in your workspace this function, which is Euler-Lagrange. And this function, where do you get it from? Correct, it's on Canvas. So we have used the same function for generating previous codes. So copy that function. Can you please adjust this code and figure? Just command me. Oh, yeah. I know. Okay. Yeah. Just bear with me for a second. Can you see now everything? So, yeah. So you should be able to see the code. Okay. Now, next thing is this code is going to take some time. The code generator function is going to take some time. That's why I added this delay. Pause function inside the MATLAB will actually pause at this point because it takes about 10 to 15 seconds for the function to be MATLAB function to be created, Simulink code to be created. So next part from here onwards is solving the differential equation using numerical solvers. Remember the first assignment, solving ODEs with MATLAB. So that's exactly happening. I'm solving the ordinary differential equation that we generated using MATLAB. T-span stands for time. I'm going to integrate the equation from time t is equal to 0 to time t is equal to 10. So 0 to 10 seconds. Now, these are the initial conditions for numerical integration. Now, what are these initial conditions? So initial conditions are, our states are theta 1 dot, d2 and d2 dot, theta 1 dot, d2 and d2 dot. So I'm gonna specify some initial condition on theta 1. Say my theta 1 is equal to 0. I would specify some initial condition on theta 1 dot. My initial joint 1 velocity is something. Then my joint 2 initial displacement is something, and my joint 2 initial velocity is something. So these are, so this is theta 1 radians per second. No, this is theta 1 radians, theta 1 dot radians per second, d2 displacement, and the d2 dot, which is the velocity of the second joint. Everyone understood this? This is theta 1 d, d2 and d2d. Can you see there are 4 states? That's why you need 4 initial conditions. Are you with me so far? Okay. Then this is the numerical integration of the MATLAB code. T, Y, I'm using ODE 113. You can use ODE 45 or whatever code you want. At the rate, the function that you are integrating, the name of this function ODE1 should be same as this function. Do you agree with me? Because this is the MATLAB function that you are creating. That needs to be integrated. So at the rate ODE1, T span 0 to 10 seconds, Y0, which are the initial conditions over here. Everyone understood this? Code it. Yes, no. ODE at the rate ODE1 is the function that we created on line number 74, which is Euler-Lagrange, and can you see in the apostrophe that ODE1? Okay. Then if you go down, this is where you are creating the plots. So this is actually plotting the solution of the differential equation. Do you remember the subplot function from MATLAB? So what this tells me is there are 4 variables. I want to plot those 4 variables in one big canvas, one big plot. So I'm going to convert that canvas into a 2 by 2 matrix. So there will be 4 plots. So it will be a 2 by 2 plot. The first plot is going to be time multiplied by time on x-axis and the angular displacement on y-axis. Are you with me so far? Second plot is going to be time and velocity on y-axis. Third plot is going to be time and d2, which is the linear displacement of the prismatic joint. And the fourth plot is going to be time and the linear velocity of the second joint. Everyone understood this? Okay. Now let's run. And then once you run, it will run and generate these plots. So as you can see, I did not add the legend or X label and Y label, but the plot, the first plot, first row, first column plot is the angular displacement on y-axis, time on x-axis. First row, second column, that plot is the angular velocity on y-axis and displays time on x-axis. This is d2 and time, and this is d2 dot and time. So just check the initial conditions. Can you see that the first initial condition was 0.5, second initial condition was 0.5, third initial condition was minus 0.1, and the fourth initial condition was 0. So that's the first state, second state, third state, and fourth state. Are you good?
Is there any way to code it so it automatically deletes our two functions it generates so we can run it over and over again? Or is-
Just say delete
Okay.
or clear. Everyone understood this. This is one of the most important lessons in robotics one. Because believe it or not, whether you solve a multi-body dynamics problem, whether you solve any variational mechanics problem, you are going to do the exact same thing. Oh, by the way, there is a dedicated course on variation mechanics in mathematics department. So if you are interested in what I did in Lagrangian and Hamiltonian, that course is going to talk about Lagrangian and Hamiltonian. Lagrangian and Hamiltonian. The course title is Variational Mechanics and is offered by Math department. I posted that on my LinkedIn. So if you like what I did here, that's what all you do in that course. Okay. Any questions on the material? And now, Lucas, ask me your questions. I'm ready for your questions now.
So, starting off the inertia you provided, you said I1 equals 1.
So assignment 4. So in assignment 4, I don't remember what I asked.
In assignment 4, I have the document right here. It's the moments of inertia are specified as I1 and I2, and both are specified as just 1.
I1 and I2 is equal to 1. Did I give you L1 and L2?
Specified L1. No, you did not specify L1 or L2, but we can find them from using the fact that we know what I1 is.
Okay. Did I give you M1 and M2?
Yes, M1 equals M2 equals 0.5.
0.5, 0.5. So if I give you M1, this I1, I was sloppy. This is IZ1 and this IZ2. So from here, you can find out L1 is equal to 1 divided by 0.5 times 12 square root. No, 12 square root. L2 is equal to 1 multiplied by 12 divided by 0.5. Anything else?
What was the R variable in the Euler Lagrange?
0.
0. Set it equal to 0.
Yeah.
What was that? What does that represent?
So if there is mass of the robot on M1 changing, then that will be a parameter because it's not going to be a symbolic constant.
Oh, okay.
It will be a symbolic variable that will change. So that's why that's the parameter. But parameter, you don't need parameter.
Do I remove it from the?
No, if you use the code exactly the way I have written.
Can you go back to I'm getting an error when I try to spot it. You define part before you use it, or you don't? Okay. Oh, Okay, thank you.
So this one's for the point mass, the RPO point mass on the end. And we're just saying that M3 is equal to 1.
So did I give you M3 in
Yes,
the,
it doesn't have a point mass.
Then-
The one you just did, I think.
yeah, so I would just say M3 is equal to 0.
And then I can't do that.
It will, you can do use the exact same code. Nobody's asking me an important question. I'm waiting for it. Yeah,
If I'm given in like an n position, how would I go about finding?
and ask any question about the assignment.
Do we need to consider gravity?
No, if your robot arm in the horizontal plane, you don't have to worry about gravity. But if you want to feel adventurous, you can consider robot arm in the vertical plane, and then you have to consider gravity. But that will throw your axis on.
It's like the assignment.
It looks like because we are looking from top.
So we don't.
So you can actually try to be smart, draw a kinematic diagram like this, and then solve the problem the way I have shown.
Is there a way to isolate the, it says like find the differential equations of motion using MATLAB. Is there a way to isolate what the equation is?
Yes. Oh, no, I'm okay, guys. You just have 1 minute to ask me the most important question. This is the differential equation. Why are you taking pictures? It's already created in your MATLAB script.
So what is the most important question?
My words.
What that tells me that you haven't tried to solve that problem. Okay, 4:15. I'll stop here. And good luck with your assignment.
Professor,
And if you have any questions after you work out the problem, I will be happy to answer next Monday. Hello, yes.
Professor, so problem 2 in the assignment 4 is not,
Problem 2, yes, not done yet.
okay, yeah.
Okay, Disha, I don't understand your question. So,
Hello, can you hear me?
but I have to stop now. Next class will start in 10 minutes. No, the most important question should come from you. So I will give you time on next Monday. Oh, Q2, yeah, what is the question about Q2? 1, 2, 3. Okay, yeah. I'm on, yeah, tell me, Disha. I have not taught problem 2. That's correct.